Hello and good morning, everyone. Today, inshallah, we will talk about a really very important topic. We will talk about optimization problems. This is really very important topic in all disciplines, either in IMS, in engineering, and in SBE. This is major thing because mainly most of the application they will try to get the best solution, not just only the applications, all of our life. We are in an endless search for optimizing our needs, our utilities, our aims, everything. This is why it's really a very important topic. So, as we already know, all of our course notes, references, you will find them on Moodle, and also the recorded lecture, you will find them on my YouTube channel. If you need anything, just let me know. I think also I've shared with you the recent PDFs on the WhatsApp group, and also you will find the updated list of PDFs on Moodle also. Once more, the agenda of today is to go through optimization, various techniques in multivariable functions. And we will go, I believe today we will cover hopefully two main topics, but I think we will stay with probably, I will see about how you react in this lecture or for the information that we are going to do in unconstrained optimization. And probably tomorrow I will finish, I will go through the constrained optimization with just an equality constraint, and this is going to be our work for this week, inshallah. So, the first thing is about optimization problems. As I told you in this section, this existence of local X, the optimality, we are searching for the extremum points, which means either maximum or minimum. So the first paragraph states that we are going to study the existence of local extrema of functions with several variables, of course, and learn some methods to determine which one of them we are going to have. So if you look at this graph represents actually a function in 3 dimensions, because when we say that in x, y, a function x and y, you know that the result will be the z value. This is why you can see it's in 3 dimensions. If you remark, these are the global maximum and the global minimum, and those points, this is for the local maximum and the local minimum. The theoretical definitions are given in this paragraph. I will go through it with you in this subparagraph. Then we will go through a bunch of problems depending on the cases. So the first definition states that if we have a function f such that the domain belongs to Rn and into R, which means we are dealing with a function in several variables in dimension. So f has a global maximum. When it's going to be? When the value of the function compared to all the points in the neighborhood, it is greater than or equal f of a. And that's for every x belongs to d. So if you get for a global maximum, you will find the value of the function at point A, it is greater than f of x all around this area, or which belongs to the domain. The same exactly applies for the global minimum, and it will happen at a point A when f of a is less than or equal all the neighborhood of point A or all the points on the domain. So this is A, my point, that's the global minimum. So if you compare this value with all the other values relative to the domain of the function, this is the peak of them. This is why it's called, it's a global minimum. So now you have the conditions for a global maximum and the global minimum. The definition of local maximum, it's really very close, but remark, it is verified in an open ball centered at A, which means it is the highest, but in the neighborhood of this point. So if this is point A, and I'm looking for a local maximum, it is not relative to the whole domain, it's just within the neighborhood of point A, and this is why it's called a local maximum. Same exactly applies for the local minimum if A is here, and if you compare this value with relative to the neighborhood of point A, which is defined, of course, by the open ball centered in A and contained in D. Same definition is in the 4.1 according to the PDF that you have. I've already sent you all of this more than once previously. So if has global or absolute maximum under the condition identified, and also it will have a global or an absolute minimum if A belongs to D and it's less than or equal f of x for every x belongs to the domain. For these two guys to be the absolute maximum or the absolute optimal point or the global optimal point, and these two conditions for the local or relative maximum. Some people call it the local maximum or local minimum, or the relative maximum or relative minimum at certain point at the neighborhood, as I told you, of an open ball. So once more, this is the main definition of the local extremes or the absolute extremes or the global extremes in general. This is really very important. For the bunch of the coming slides, we will talk about the basic concepts that we have to put in mind if we are trying to find an optimal solution for an optimality problem. The first thing is a clear understanding of the problem. So first of all, you need to read your problem scenario more than once, understand the situation very good. What are the limiting if constraints if applies? If it is not, if there is no constraints, you have to put this into your mind. So in this case, in this step, we determine which type we are going to analyze. But the beginning is understanding of the problem. Understudy should understand it very well, along with an accurate mathematical formulation, or what we call a mathematical modeling for the problem. Identifying the objective function, determining the constraints if exist, determining the decision variables, as you will see, and so on. So, as I told you, it's essential for effectively solving an optimization problem. This involves the identification of the relevant variables, which are the decision variables, the constraints if they exist, and to try to satisfy them. Otherwise, your solutions is not going to be visible. Okay, which makes sense, as usually, as clearly definition of the study of the objective function. So if I want to maximize or minimize, for example, I'm maximizing the profit or maximizing my revenue or minimizing my costs, subject to x1 up to xn, which are the constraints who are functions in the decision variables, as you will see. So x1 up to xn are the decision variables, the variables of the problem, where x belongs to or n in the constraints set of possible values for decision variables, and it is defined, as you can see, by the problem constraints. Also, it will be more obvious from this slide if I want to maximize my function subject to a bunch of constraints. So x1 up to xn are the decision variables, x belongs to n are the constraints, and the function in the decision variables is my objective function, which is required to be maximized or minimized. Maximization to increase my profit, to increase my revenue, and minimization if, for example, I want to minimize effort, I want to minimize costs, and so on. So, as I told you, those are the unconstrained. There is, in this slide, yes, I would like to give you an idea about the possible cases or of optimization problems. We have actually three types of optimization problems. The first of them, which is going to be our topic today, is the unconstrained optimization. So I need to optimize a function with no limitation on this function. there is no constraints. There is no boundaries that will bound my solution other than the domain of this objective function. So in the unconstrained optimization, there are no constraints for the problem decision variables. That's x belongs to Rn. The other one is optimization, or the second case is optimizing certain function, but it is already subject to a bunch of constraints. There is conditions I will have to satisfy first, and then get the optimal solution under these conditions. Where the constraints set is defined by independent quality conditions or equality conditions. So you will have your objective function, then a bunch of conditions you will have to satisfy in order to get your solution of this optimization problem. The third type is optimization problems, but not with equality constraints, with inequality constraints. And here I have more degrees of freedom. Usually in this part, I'm covering a part of a curve, I'm covering a polynomial or a straight line or something like this for a bunch of points, and I need the best solution in this curve. But in this case, I'm talking about a visible area, as you will see down the road, either in this course or in other courses, like operational research or something. You will be optimizing your function, but within a specific interval that's gonna be determined by the various constraints that you will face in the formulation. So, the first thing that I will have to do is to read my problem very well, trying to understand the type of optimality that we are dealing with, if it is constrained, unconstrained, because it will affect the method of solution, as you would say. As I told you, our topic today is about the unconstrained optimization. So I'm just trying to get a scheme or an algorithm how to deal with those types of functions where no additional constraint or additional function I will have to satisfy first before I start optimizing my problem. This is really, as I told you, is a very important point. So let F is such that D belongs to R into R, and the A belongs to the interior of your domain. If F is differentiable at A, and the first derivative of your objective function at the point, at certain points equal to 0, then A is called a critical point, or sometimes we call it a stationary point. So at this point, I will have to give an extra attention, because it may be a local or global or not even a critical point. From here, we will go to the main theory, which states that starting, let F be a function of class Cn in an interval, and A belongs to this interval. If F dash equal to F double dash, blah, 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 all of them equal to 0 at certain point, I will start differentiating till I find the first derivative, or I'm sorry, the first non-null derivative. So if it is the first, second, third, fourth, fifth, whatever, if it is not equal to 0, then according to the rank of your derivative, is it the second derivative, third derivative, fourth derivative? As we will see, this classification applies. So if the first non-null, derivative of your function at the point of discussion is even number, then I will look to the value of your function. If it is the value of the derivative at this point, if it is less than the 0, which means a negative value, then I'm dealing with a local maximum. If the nth derivative at this point is greater than 0, then it has a local minimum, as you can see. Type, what if n is an odd, the order is an odd? It means the third derivative, the fifth derivative is not null. In this case, your function at this point, it's an inflection point, it's not a critical point. This is mainly the main theory that summarizes a lot of cases and a lot of special cases that may arise. I believe I've arranged our analysis to go starting from functions from to R first, then we will go to multivariable functions. So let's test the water for this theory and let's go through this example. This is really a very simple example. It's a cubic polynomial. As you can see, it's a 3x cubed plus 3x squared plus 2, which is, this is the function that's required to be optimized or to determine at which point belongs to this, the domain of this function, if I have an optimal solution or there is no optimal solution in this case. So I will start my analysis. As you can see, I will determine the critical point and identify their nature. So the first step is to start to get the first derivative of this function. So that's the first step. So if we want to start differentiating, it's going to be 9x squared, as you know, as you will see. It's really very simple. You will find 9 of an x squared, then plus 6 of an x, and this is the first derivative. This is the first step. Second step, I will put this derivative is equal to 0, and then try to seek these points. So as I told you, the first step is to get the first derivative, then put it equal to 0. So if I get the first derivative, as we saw, it's going to be 9x squared plus 6 of an x equal to 0. Take x as a common, so you will have 3 of an x, or 3x for example, you will have 3x plus 2. In this case, the first derivative will equal to 0 in two cases. The first of them, it is either x equal to 0 or x is equal to negative 2 over 3. So these are the two proposed cases where your function is going to equal to 0. Either x is equal to 0 or x is going to equal to negative 2 over 3. That's the two cases that we will work with. The second step is to get the first non-null. So if I start differentiating this function, it's going to be an 18 over x plus 6. And so this is the, as I told you, these are the 2 points exactly as we did. And that's the second derivative that I will test. So all I have to do is to get the second derivative as I told you. So it's going to be 18 over x plus 6. Then I will make a substitution using these points. That's a probable point and that's another probable point. If I substitute it with 0, for example, so it's going to be 18 times 0, which is 0, plus a 6, which is greater than 0. That's the first non-null derivative. In the second, it's an even one. And the value is positive, and hence I will have a minimum point at x is equal to 0. So for this function, when x is equal to 0, I will have a minimum point. If I want to get the value of the function at this point, what I have to do is to substitute in here. So replacing x by 0 and x by 0. So at the point x equal to 0, y is equal to 2, it will represent a minimum point. Same steps exactly, I will do them by replacing x by negative 2 over 3. So if I replace x by negative 2 over 3, and then make the substitution, it's going to be 18 times negative 2 over 3. So 3 was 18 is going to be 6 times negative 3 is going to be negative 12, plus 6 is going to be negative over 6. And this is why you can see at negative 2 over 3, it's negative 6, which is less than 0. So once more, the first non-null derivative is the second derivative, and the value is less than 0, so it's going to come up to a maximum point at this, at x equal to negative 2 over 3. And this is the general idea about identifying the critical points and the nature of these critical points. As you can see, the first is to put the first derivative, the first step is to put the first derivative is equal to 0, then the second derivative, and then to use these critical point or stationary points in the substitution in the first non-null derivative, as you can see. Another problem, which is x cubed over 3 minus 1. So if I want to do exactly the same analysis, in order to determine the nature of the critical points, and if they exist or not, I will do exactly the same. So the first is to find, or the first step is to try to get the first derivative. So start differentiating this function. So it's gonna come up to 3x to the power of 2 over 3, which means x to the power of 2. So that's the first step. Get f dash x and put it equal to 0. So it's gonna be x squared equal to 0. So now I have a proposed point, or a point that it may be or it may not be a critical point, which is at x equal to 0. How to be sure? I will start differentiating the second derivative, or more than that, trying to search for the first non-null derivative, as I told you. So I will start differentiating. F double dash x is equal to 2 over x. So it's going to be 2 times x. That's the second derivative. Unfortunately, if you try to substitute with 0, it's going to equal to 0. So I will need to do an extra derivative. So I'm differentiating for third time and trying to substitute. Once you differentiate for the third time, this value is going to be 2. So that's the value of the third derivative. The value of the third derivative is 2. So the first non-null derivative is the third derivative. In this case, I don't have a critical point. I have an inflection point, or as I told you, this is not going to be a local extremum. I will have inflection point, as I told you. If the first non-null was an even derivative, so for example, if this x cubed was x to the power of 4, for example, then at the third derivative will equal to 0, and if you try to get the next derivative, which is the fourth, it's going to be positive, and then hence I will discuss or try to substitute to see what's going to happen. But as you can see, the steps are very, very clear. Get the first derivative, probable points that may be critical points or stationary points. Get the second derivative, try to substitute, not a value equal 0. Get higher order derivative, and then substitute regarding and remark the sign of the value of the function after your substitution. If I look for this problem, which, as I told you, it's a fourth degree, let's differentiate the first derivative for this function, as I told you exactly. So once we do this, you will find that x is equal to 0, which is a stationary point or a probable critical point. So I will leave it, and then I will go to the second derivative and see. So if you differentiate once more, it's going to be 12x squared. That's the second derivative, as you will see, 12x squared. So if I make the substitution x equal to 0, and then make the substitution here, replacing x by 0, so it's going to be 12 times 0, which is 0 also, which means the second derivative is a null. So I will have to differentiate more, getting the third derivative, differentiating more, which is going to come up to 24 over x. Still, if you try to substitute at x equal to 0, the value is going to equal to 0. Once more, I will need an extra derivative. So the first non-null will appear to you not at the third, but at the fourth. Look to the rank or the number of derivatives. That's an even number. Since it's the first non-null derivative is an even derivative, and the value is greater than 0, so probably at x equal to 0, or it is a critical point as x equal to 0. So once this is greater than 0 and the order of derivative is not null, is 4, which is even, then I will have a local minimum. The strategy is really very clear. The steps that we follow: getting the first derivative, put it equal to 0, get critical point, get the second derivative. If it is not null, then start substituting. Greater than 0, minimum, less than 0 is going to be maximum. If the second derivative is equal to 0, I will have to search for the first non-null derivative, identify it, look to the number of integration, or the number of differentiation, if it is the third, fourth, whatever. Determine this value. After this, you will decide if it is a critical or minimum according to the theory, as you can see. Once we go to Rn, the process will be similar to what we did go through, but we will have to deal with the complexity of acting and working with functions in several variables. And this needs an extra attention from us. So the first thing, let's begin by considering n is equal to 2, which is the beginning of the multivariable functions, or functions in several variables. So it's an a and b. So start, if there exists a local maximum or a local minimum, so all I have to do is to follow the following steps. The bottom line, get your function, get the gradient of your function is equal to 0, which means you will need to get both partial derivatives of your function and the bottom them equal to 0. Once you get your first derivative or the gradient vector equal to 0, this is the derivative of the function with respect to x, the derivative of my function with respect to y, both them equal to zeros, then this is the equations that will develop the critical points or the stationary points. After determining this or those points, then I will try to get a higher derivative. So if this is the function that we are dealing with in 2 dimension, like the elliptic paraboloid that you see, these are the main steps in order to identify. So the first order derivative in multivariable function is the gradient vector. So as I told you, get the gradient vector of f bottom equal to 0, determine the critical or stationary points, then I will follow the following relation. Remark that I will work either with the differential equal to 0 or the gradient equal to 0 in order to identify the critical or stationary points. Then, for the second order conditions, I will get either the second differential. Do you remember what's the second differential? The second differential, it means I will try to get my Hessian matrix. I would like to introduce this for you. Already we did this previously. So if this is dx, this is dy, this is our Hessian matrix, and then this is a dx and dy. Of course, this is partial 2f partial x squared. This is partial 2f partial x partial y, partial 2f partial y partial x, partial 2f partial y squared, which is the Hessian matrix. So, according to the differential, if you expand these equations, you will find your differential states that it's a d2, okay? It's a d2 of x times partial 2f partial x squared plus partial 2f partial x partial y times 2, and in this case you will have dx and dy plus, as I told you, partial 2f of partial y squared, and this is the second differential, as I told you. If your second differential is less than 0, then f of a is a local maximum. If the second differential is greater than 0, then f of a is going to be a local minimum. If the second differential is greater than 0, and in some points, and the first and the second derivative of a less than 0, then f is not an extremum point or a saddle point at this point. These steps are really very important, and that's the bottom line of the steps that we will see in the coming slides. So once more, exactly as we did in this slide or explained, we will go through the next step. The problems will appear if the value of the point at the second differential is equal to 0. Like if the second derivative is equal to 0, and I will need to do extra search for the next non-null derivative. It is exactly here, but it will be on a larger scale. So if the second order conditions, okay, greater than 0 or greater than or equal to 0, that's the second is negative or positive, semi-definite quadratic form, and in this case, the analyze will be singular directions, and we will have an extra analysis. Okay, and also of D2F is equal to 0, we will do the same. For the cases number 4 and number 5, I'm not gonna include them for this year in our study. It will be sufficient for us to study the general cases, the first order condition, the second order conditions. In the case of, as I told you here, I will study just only the positive definite or the negative definite cases. I will get away from the indefinite case because of the complication of the case, and I don't want to spend plenty of lectures in this part. But I've already attached this PDF or this slide to your slides. If you need and more details, you can read about them. As I told you, the following graph illustrates the case of critical points. That's a local extrema or a saddle point. That's when it is, as I told you, semi-definite. But if it is positive definite, if it is not positive definite or negative definite, probably I will need further analysis, and that's one of the cases that I may have a value of the function in some of the curves or in some of the directions are positive, and on the other are negative definite, as you can see. Okay, so once more, this is the second derivative, okay, the second differential, I'm sorry, and that's our Hessian matrix as I wrote it to you, and these are the second order differential in specific. This is our Hessian matrix, the one that I'm showed in the previous slide. We need to determine or to classify this quadratic form, or to classify the Hessian matrix if it is positive definite, negative definite, or indefinite. The semi-indefinite cases we are not going to study, as I pointed out in the previous slide. So, and that's really simplifies your life a lot. All you have to do is to try to identify if the Hessian matrix is positive definite, or if it is negative definite, or it is indefinite. And so it's an easy task to go through it using the leading principal minors, or the principal, using the principal minors. It's going to be really very simple task compared to the study that contains the semi-definite cases. So once more, a quadratic form is a polynomial that only has the terms of degree over 2. I need a quick revision about the quadratic forms. So for example, if I have x squared, 2 over xy, 2y squared, if I want to put my quadratic form on a matrix form as this one, it's really very simple. I will take the elements, the coefficients in front of x squared to be the element 1, 1. I will take the coefficients, the coefficient in front of y squared to be the element 2, 2. Then for this value, which is x and y, I will divide on 2 and put the half of it in the 1, 2, and the other half in 2 and 1. And this is the shape, as you can see, of my definite, of the Hessian matrix, as you can see. So it's really very simple just to do this. This is x and y. That's the matrix 1 and 2, negative 1 and negative 1. And this is x and y, as you can see. So it's really very simple. If I want to do it with a polynomial of 3 and 3, or if I have 3 variables, it's gonna be exactly the same. I want you to remark that if I want to get this matrix, it's very simple, and we already did that plenty of times in linear algebra previously. I taught you linear algebra, so I know what we did go through all of this in details. So for the coefficient in front of x squared, it's gonna be 1, 1. For the coefficient in front of y squared, so it's gonna be at 2 and 2. For the one in front of z squared, it's gonna be on the element 3 and 3. This is -5. Then this is the coefficient, half of the coefficient of xy. This is half the coefficient of xz. So here I'm searching for an xy. There is no, so it's gonna be 0 for xy and 0 for yx. But I still have xz. So it's gonna be the first and the third place. So it's an A13 and the A31. I will take half of it. So it's gonna be 2 over here and 2 over there. Then for this position, this is the position of the coefficient of y times z. Since I don't have y times z here, so the coefficient is 0, so that's the shape of the function, of the matrix, as you can see. This is really very important. If I'm writing the Hessian matrices, the Hessian matrices is going to be exactly the same. The Hessian matrix for a 2 by 2, as you know, it's going to be partial 2f partial x squared, then partial 2f partial of x partial y, partial 2f partial y partial x, partial 2f partial y squared. And for this guy, it's gonna be on this form: partial 2f partial x squared, partial 2f partial y squared, partial 2f partial z squared. And for this guy, partial 2f partial of x partial y, partial 2f partial x partial z. And on the vertical x, you will have partial 2f partial y partial x, partial 2f partial z partial x, as you can see. And for this guy, it's gonna be partial 2f partial y partial z, then partial 2f partial z partial y, and that's the Hessian matrix once more for a 3 by 3. All of this was covered briefly.